Okay, so can you hear me and do you see what is in presentation?
Yeah, we can see.
Okay, perfect then. Whenever you...
Great. So yeah, we'll continue with Stefan talk, who will tell us about Systolic S1-index and characterization of non-smooth Zoll convex.
So thank you very much for the invitation to speak at this Zoominar. It's a great pleasure. And today I will talk about basically a way one can extend definition of Zoll convex bodies to a non-smooth setting in a way which is natural from symplectic point of view. So first I will briefly give a definition of Zoll convex bodies in a smooth setting, and then I will bit motivate results which will follow. So we start by taking standard Liouville form on R2N and standard symplectic form. And then for now, we consider a bounded convex domain or convex body with a smooth boundary. And we also ask that origin is contained in its interior. So in this case, we have that basically radial vector field is transverse everywhere on a boundary. And because this is basically Liouville vector field for lambda 0, we get that C lambda 0 is Liouville domain, which means when we restrict this lambda 0 to the boundary, we have a contact form. And in particular, we have a Reb vector field given by the standard system of equations. So now we can define what it means to be for a convex body to be Zoll. So we say that C is Zoll if all Reb orbits on a boundary are closed and share a common minimal period. So in general, what is true is that if all Reb orbits are closed, they must share a common period, but this period does not necessarily have to be minimal. And we call the Reb orbits which have minimal period systoles. So being Zoll just means that basically space of systoles covers all the boundary. Okay, so now to give a bit of motivation, I need one more definition. And this definition is definition of strong convexity. So in a smooth case, we say that C is strongly convex if sectional curvature is positive everywhere on the boundary. And now I will recall some result from Ginsburg, Gurel, and Mazzucchelli from 21, which states the following. So smooth and strongly convex body is Zoll if and only if first Eckland-Hofer spectral invariant is equal to the nth one. So these spectral invariants were introduced by Eckland and Hofer in 1987, and they are kind of defined for convex bodies. And one thing which is not clear for these spectral invariants is whether they are a monotone with respect to symplectic embeddings. And then we come to the next result, which is a theorem from my previous work from last year, which states that for convex bodies, basically these Eckland-Hofer spectral invariants are good Hutchings capacities. And I will make a maybe small break here to see if there are any questions regarding these statements. Okay. So if not, then I will continue. So what do we get from here? We get a next corollary, which states that smooth and strongly convex body is Zoll if and only if first good Hutchings capacity is equal to the nth one. Now, what is particularly nice about these capacities is that they actually stay monotone with respect to symplectic embeddings of interiors, which means in the context of this corollary, one can interpret it in the next way. So whether something is Zoll or not depends only on geometry of interior. And in particular, we get the following corollary, which states that if smooth and strongly convex body is such that its interior is symplectomorphic to interior of a ball, then C must be Zoll. So the point of this project was to see what this condition with capacities impose on a space of systoles in non-smooth setting, and can we in some sense extend the definition of Zoll to non-smooth setting. So the second part of talk will be about that. So we return to our Reb vector field and just introduce notation for set of closed Reb orbits. And the spectrum, which in this case is just a set of periods of closed Reb orbits. Now in a non-smooth setting, we don't actually have a Reb flow, so we have to figure out a different way to define sort of a closed Reb orbits, and this is how we're gonna do it. So this is basically another way to see Reb orbits in a smooth setting. So we define positively two homogeneous function, which is one on a boundary. And then by simple calculation, one can basically easily show that Reb vector field is basically gradient of this function multiplied with J0, where J0 is standard complex structure. And therefore, we can see closed Reb orbits as the solution of this equation, where T is now period of Reb orbit. And one more notion I want to introduce is notion of action. So when we have a loop, we define action of that loop just as an integral of lambda 0 over that loop, and this is independent of reparametrization up to changing a sign. So we now consider space of closed Reb orbits as we just change basically parametrization. So we put parameter space to be one torus, and then this T pops up in front. And we can see that spectrum is basically action over this set. So why is this nice for non-smooth setting? Well, because as I said, we don't have Reb vector field in a standard sense, but this function HC still makes sense in a non-smooth setting. So now we have any convex body, and what is true is that this function HC is basically convex function, and they are quite nice in a sense that they are, for instance, locally Lipschitz, which means they are differentiable almost everywhere. But also, if they are not differentiable at some point, there is still notion of subdifferential. So subdifferential at some point is given by this inequality here. And it's always non-empty convex compact subset. And if function is differentiable at a given point, then this is just a set which contains basically gradient. So then we have natural extension of closed Reb orbits, which we're gonna call the generalized closed characteristics. So set of absolutely continuous function which satisfy this equation almost everywhere for some constant t. And now, as you can see, this is the same equation as it was in a smooth case, just that instead of gradient, we have here now subdifferential. And basically, because now this subdifferential is a set, instead of equality, we have that gamma prime of t belongs to a set, because now this subdifferential is a set. And moreover, we can make sense of systoles as the subset of generalized closed characteristics, which have minimal action. So in particular, if we fix some generalized closed characteristics, it will belong to the space W1 infinity, so it will have a finite action, and then we just take a subset of this characteristic with minimal action. It is always non-empty. This was shown by Clark. And then another thing I want to introduce here is space of centralized systole. So we just take L2 orthogonal projection onto the curves with zero mean, and we just consider a space of centralized systoles, so just take projection of the space of systoles with this map. One can also see it as a space of derivatives of systoles if one want. And then most important thing at this part for these spaces is that they actually possess natural S1 action. So we have natural S1 action on these spaces given just by reparametrization, and therefore to the space of systoles and centralized systole we can associate some topological invariant called Fadell-Rabinowitz index, and for that we need S1 equivariant theory. So first we have to define S1 equivariant cohomology to see what does it means. So we take now S1 space, which means, for instance, we have a paracompact topological space on which we have S1 action. That action does not need to be free. but we want to make it in a way free. So we choose a contractible S1 space on which we have a free S1 action. So for instance, that can be S infinity. And then when we consider a product of these two spaces, because ES1 or S infinity is contractible, it's homotopic to X. And then in addition, if we consider diagonal action on a product, it's free because it's free on S infinity. So now we define S1 equivariant cohomology just as a cohomology of S1 product of these two spaces. And the next thing shows naturality of the definition. So if we have free action, this S1 equivariant cohomology is just a cohomology of a quotient. And now we can define Fadell-Rabinowitz index. So quotient of this S infinity will be CP infinity, and we can consider a map from S1 product of X and ES1 to BS1, so just projection onto the second coordinate. And this will induce mapping cohomology from cohomology ring of BS1 to S1 equivariant cohomology of X. Okay, and this cohomology of BS1 is just a polynomial ring generated by a polynomial of degree 2. And we can pull back the generator and then look when it disappears, basically with respect to cup product with itself. So this is what Fadell-Rabinowitz index is, and because here we have a shift by 1, it will always be bigger or equal than 1 for a non-empty set, and we set it for empty set to be 0. And in particular, I said, yeah, so I forgot this part. So so if we have this is important property of the Fadell-Rabinowitz index. So if we have a map which preserves action, meaning it's S1 equivariant, then Fadell-Rabinowitz index of the domain is smaller or equal than Fadell-Rabinowitz index of the codomain. So in particular, in our case, for spaces of systoles and centralized systoles, because this map pi 0 is S1 equivariant, we have that Fadell-Rabinowitz index of the space of systoles is in general smaller or equal than Fadell-Rabinowitz index of centralized systoles. Now we have to choose topology here, but I will talk a bit about that in a while. So the other inequality is not clear in general. And now we're coming to the section with the main results. So first we will give following definition. So if we take now any convex body and consider its translation such that the translation contains the origin, we define Systolic S1-index as the Fadell-Rabinowitz index of the space of centralized systoles where topology we take to be induced by the uniform norm. And this is well defined, which one can see from the following theorem. So if we have a convex body whose interior contains the origin, then it basically holds that Fadell-Rabinowitz index of this space of centralized systoles is equal to the maximum over K, where kth Gutt Hutchings capacity is equal to the first one. Now, why we chose uniform norm? I think that this should be important to explain. Well, because in a uniform norm, we have that space of systoles and centralized systoles are compact, also in a non-smooth category, and uniform norm is actually equivalent to the weak star W1 infinity norm. And being that space of systoles is bounded in W1 infinity norm, one can then ask, can one do better with the topology in a sense that one keep this compactness property? And the answer is no. So one can find example, for instance, Lagrangian product of ball in L1 norm and ball in L infinity norms give example where a space of systoles is not compact in a W11 norm. So this sort of fails. And then the other part of theorem says that if we have strictly convex body or boundary is smooth, we have that Fadell-Rabinowitz index of the space of centralized systoles is Fadell-Rabinowitz index of the space of systoles. So in general, we don't know whether this equality holds. So in strictly convex case, this holds because the basically space of centralized systoles and space of systoles are S1 equivariantly homeomorphic, so they are same, which doesn't hold if one drop the strict convexity assumption. Example for this can be polydisk, but also one can find a smooth example. And actually, the part where boundary is smooth is non-trivial to prove. So to prove other inequality, and there we use basically Eklund-Hofer capacities and relation with some Clark duality. So, and boundary really have to be smooth for the approach I used in a proof because it requires that spectrum cannot contain interval, which can happen actually if you assume basically any regularity if you allow dimension to change. So basically from this theorem in particular, we get that systolic S1-index is well defined, and we get this formula here. And this gives us, not to forget to mention that also one can see the characterization of systolic S1-index with Eklund-Hofer capacities, which coming from the recent work of Gutt and Ramos. They basically show that Gutt-Hutchings capacities are same as Eklund-Hofer capacities in a class of star-shaped domains. And from the basically formula for systolic S1-index, we can see that actually it is a symplectic invariant. So more precisely, if we have two convex bodies such that their interiors are symplectomorphic, then they have same systolic S1-index. And some other things we get for this index. So if we consider now systolic S1-index as a function in the space of all convex bodies, first of all, it will be well defined, so always be finite, because Gutt-Hutchings capacities goes to infinity as k goes to infinity. And then if we consider Hausdorff distance metric, this function will be upper semi-continuous, and we can find uniform bounds in general using John ellipsoids. It is not very optimal, but I mean, it is what it is. And then for S1 and invariant convex bodies and in a smooth category, we can get optimal bounds, which are achieved, for instance, for a ball. So now why this invariant is interesting is because it is related with the Zoll property in a smooth case. So we define generalized Zoll convex bodies as the convex bodies which satisfy the inequality that systolic S1-index is bigger or equal than n. So Fadell-Rabinowitz index of the space of centralized systoles is bigger or equal than n. And then we have following theorem. First of all, a convex body is generalized Zoll if and only if first Gutt-Hutchings capacity is equal to the nth one. So this we get from the characterization of systolic S1-index with capacities. The second statement is that convex body with a smooth boundary is generalized Zoll if and only if it is Zoll. And this we get because we were able to prove basically that space of centralized systoles is the same as the space of systoles when boundary is smooth. So we can remove strong convexity assumption from the corollary at the beginning, if you remember. And the third thing we get is that basically this space of generalized Zoll convex bodies is closed in a C0 topology. Okay, and then natural thing would be next corollary. So if the interior of a convex body is symplectomorphic to the interior of a ball, then C is generalized Zoll convex body. And in particular, if the boundary is smooth, then C must be Zoll. And one thing to mention that in a S1 invariant category, the only generalized Zoll convex body is a ball. And then I want to reflect this corollary to Viterbo's conjecture, which states basically that for any convex body, first Gutt Hutchings capacity is smaller or equal than n factorial times the volume of that convex body, and moreover, the equality holds if and only if interior of C is symplectomorphic to interior of a ball. Now, this first Gutt Hutchings capacity in a convex case is basically action of a systole, and we know that Viterbo conjecture actually fails in general, so in a class of non-symmetric Lagrangian products, but still stays sort of open as a conjecture in a centrally symmetric case. So that Viterbo conjecture fails, it was shown by Hein, Kislev, and Ostrover. But then regarding the previous corollary, we see that generalized Zoll convex bodies are natural to study in a sense of this Viterbo conjecture, at least in a second part. But also there are some partial results where people show that basically these, at least in a smooth case, that Zoll convex bodies are local maximizers of systolic ratio in a C2 topology. So maybe also in a context of first part of conjecture. So it is not known generally if one go to non-smooth setting, what would be systolic ratio of generalized Zoll convex body. So whether one can maybe assume, I mean, hope that they're all symplectomorphic to a ball, or maybe something exotic can happen. So this is in a way open. So I would maybe finish with this. So thank you very much for your attention.
Any questions?
I have a question. Can you hear me?
Yeah.
So do you expect that it'd be easy to prove that a generalized Zoll convex body can be approximated by a smooth Zoll body?
Oof. I think that it's very tricky, because I mean, at least at this point, because one doesn't really know what this Fadell-Rabinowitz index on a space of systoles means. So one cannot even tell what. I mean, for instance, natural question would be whether, I mean, at least through every point systole passes or something like this. So at this point, one really does not really even understand dynamics on a boundary. But if one understands that, maybe this is true. I don't know. I mean,
because that would probably help to prove that the interior of a generalized Zoll convex body is symplectomorphic to a ball.
Yeah. I agree. I mean, it would be something. I mean, one can consider also this closure of smooth Zoll convex bodies, and the closure will be consisting only of generalized Zoll convex bodies. So then one can see
a closure in what topology?
Is C0.
C0. Yeah. Cool. All right. Thanks.
You're welcome.
Do you have an example where the index is strictly greater than n?
No, I think this would be very exotic, because for instance, I mean, I don't know whether it holds, but I mean, if index is, for instance, n+1, then cohomological dimension of the space of systole would be greater than cohomological dimension of the boundary, which would be weird. But also from symplectic perspective, it would be exotic. For instance, the ball capacity could not exceed 1/2 of the Gutt Hutchings capacity. So I personally don't believe that. I mean, there exists a convex body with a strictly greater Fadell-Rabinowitz index, but I mean, it can happen. I don't know.
Thank you.
You're welcome.
Can you prove the local maximality of the Viterbo for generalized Zoll? It's known for smooth Zolls.
that's I mean, there are some indication that this characterization with capacities could help. So, for instance, if one considers smooth Zoll convex bodies, no, then if there is a convex body which is a strict subset of a generalized Zoll convex body and have the same first capacity, it must follow that it's generalized Zoll convex body. So this would imply, because one can then find a smooth, that it's Zoll. So this cannot happen, for instance, because I mean, we know that systolic ratio is always the same for Zoll. So for instance, if they exhibit a property that they have, for instance, locally constant systolic ratio, I mean space of generalized Zoll convex bodies, then I would expect that they are sort of local maximizers in C0 topology. I mean, at least it would have to happen that for every convex body which is strictly smaller than a convex body, generalized Zoll convex body, the first good Hutchings capacity would have to be strictly smaller than a first good Hutchings capacity of that convex body, which would be in some sense necessary condition. But then to connect it with the volume would be different. I don't know. I mean, this is how I see it at the moment, but I'm not sure I answered your question.
Okay. Thank you, and thank you for all the speakers today.